behind mean flow velocity is the Darcy-Weisbach equation. This, like many of these other equations, was originally derived for pipe flow, but then has been modified for open channel flow. The reason I'm going over the Darcy-Weisbach equation is a little bit less for the form of the actual equation itself, and a little bit more for the definition of the Darcy-Weisbach friction factor, which turns out to be a really convenient way of expressing relationships between shear stress and velocity. So you might remember from earlier on that we discussed the definition that tau b, which is the basal shear stress, is equal to the density times the shear velocity squared. And so that's just a definition. And I'm going to write it here just so we have it together with this next equation. So we have tau b equals rho u tau squared. Oh, I wrote a star because usually in my world u star is shear velocity, but we use stars also for dimensionless numbers. So I'm trying to reform myself and create a little bit better nomenclature, a little bit easier to understand, especially when you're new to these things, of having use of tau for shear related velocity. So what you can see down here is that there is this other term, so c sub f. And so what that means then is, if we compare what these two equations, that c sub f u bar squared equals, by definition, u tau squared. And so this friction factor essentially exists to translate between mean flow velocity and the shear velocity. If we consider a steady, uniform open channel flow in a channel that's much wider than it is deep, so instead of using hydraulic radius, we just use depth, we have u tau is equal to the square root of GHS. And so we can define exactly what this term should mean. And that becomes very useful again. So we have u bar is equal to u tau over c sub f, right? So we can just look up here. Right? Which is equal to g hydraulic radius slope over this friction factor. And then, of course, we can say that tau sub b is equal to rho times c sub f times, and this is just actually a quick check to see if we get everything back. Let's see. So then tau b is equal to rho cf times u bar squared. So this is going to give us g r sub h s over c sub f, and the square root and squared cancel out. So we have this canceling out, and then we have basically just rho times g rhs. So that goes into u tau over here, right? And so then we end up just coming back with tau b is equal to rho u tau squared. And I apologize that I have a h here and a rh down here. Those are meant to be basically interchangeable. So from this then, we can actually see, so since we know that, so since we know from this that we have u bar is equal to this 1 over square root of Darcy-Weisbach friction factor times square root of GHS, which is u tau. And so this is going to be the Darcy-Weisbach approach. We also have the Shazy approach, which is u bar is equal to the Shazy coefficient times u tau. So these expressions are actually very similar, but the key thing here is that because of how the Shazy coefficient is written compared to how the Darcy-Weisbach coefficient is written, that we can create this relationship between velocity squared and shear stress. And this is going to be an important way to think about shear stress and think about its relationship to velocities in the flow. And So we're going to think about this in two separate ways just now. First off, we're going to talk about the units like we have before. Or second off, we'll talk about the units. And then first off, before that, we're going to talk about how this equation behaves in the limits. So as you can see, we have u bar equals square root of GHS over C sub f. And so pretty easily we can see that at h equals 0, u bar equals 0, so check and good. And at h equals the Bank-full depth, which is what this is. So this is the Bank-full stage flow depth, the flow depth when the channel is filled to its brim. And so this is the highest depth that can exist in that channel. So when h is equal to this deepest depth, then we have u bar equals square root of GHBF(S) over the Shazy, the Darcy-Weisbach friction coefficient. And this Darcy-Weisbach coefficient in the denominator is just a constant or is a coefficient that might vary somewhat. We're going to see that down here. And so what we essentially get is that when we have these deepest flow depths, we then also have the highest velocity. So that also checks out. And so then let's solve for the units of the Shazy friction factor. Well, since we just have u bar equals u tau over square root of CF, we know this is units of velocity. This also has units of velocity, so CF is unitless. Empirically, Leopold found that the Shazy friction factor is proportional to the flow depth. And so you can think about this like Manning's equation. And that's kind of like this h to the 2/3 factor. And then it also had this proportionality to grain size. And so we can think of this as roughness. This is the 84th percentile grain size on the bed. And bigger grains lead to more roughness in the flow and lead to more flow resistance. So this overall tells us that we still have this ratio between flow depth and grain size, where if the flow depth is bigger compared to the roughness elements, then we have less frictional resistance. If the flow depth is smaller compared to the roughness elements, then there's more frictional resistance. So just a few closing thoughts about not just Shazy, but all of these different formulas. So we have not just Darcy-Weisbach, but all these different formulas. We have the Shazy coefficient, Manning's N, and the Darcy-Weisbach bed resistance coefficient, which is equal to the Shazy coefficient to the -2 power, right? So we have Darcy-Weisbach, so 1 over square root of Darcy-Weisbach is equal by definition to the Shazy coefficient. And then Manning's N, we can see the relationship between these two from that equation I had from the Gary Parker paper. And from those relationships, you can then create the relationship between Manning's N and the Shazy coefficient. All of these are some semi-empirical approaches to try to figure out what mean flow velocity is. And so next we're going to work on Prandtl mixing and the law of the wall to figure out how we would actually represent the full velocity profile and more rigorously derive what flow velocities should look like inside a open channel. And from that, the goal is to create a much more formal expression for flow velocity that might be practically actually just as useful as the Manning equation, but in some ways more satisfying because there's more physics involved and there's a more exact way of approaching a more exact solution that includes some of what we've learned earlier about turbulence.